In this video, I'm going to take a very basic look at how the inverse of a relation will affect its graph. Okay, so what I'm going to do is just start with a number of ordered pairs. So this is going to be pretty basic here for this first one. Like 2, 3, -6, 4, 3, 6, 1, 1, and 5, -3. And the inverse is created by switching the domain with the range, or another way to say that would be that we're just switching the x values with the y values. So if this would be our function over here, f of x, then the inverse, or f inverse of x, would just be the resulting ordered pairs if I switched all of the y's with all of the x's. So if I start here with 2, 3, actually, you know what? Let's not get ahead of ourselves. I'm going to graph the original function here first, and I'll graph this in red. So we'll start by graphing 2, 3, which will be right here. I'm just going to graph all these points. -6 and 4 would be right here. We've got 3 and 6 would be right here. I've got 1, 1, which would be right here. And I've got 5, -3, which would be right here. And that would be the picture of what this graph would look like. Actually, you know what? I think I got one point here just a tiny bit off. It would be this one here. So it should be 3, 6, not 2, 6. Let me make that quick change. Okay. Now that I've got that all set to go, I'm going to graph the inverse in green, but first let's go ahead and we're going to just flip-flop all of these ordered pairs to see what the inverse looks like. So the point 2, 3 becomes the point 3, 2. The point -6, 4 becomes the point 4, -6. You get the idea, so I'm just going to flip all the x's and the y's here. And now that I've got them all flip-flopped, I'm going to regraph these in green to show what the inverse looks like. So instead of having the point 2, 3 here, I'm going to graph the point 3, 2, which is right here. Then I'm going to graph the point 4, -6, which would be down here. Then I'm going to graph the point 6, 3, which would be right here. I'm going to graph 1, 1. Notice that 1, 1 actually, since the x and the y are the same, it's actually the exact same point. So this point's kind of overlapping here. This is both inverse point and in the regular function. And then we've got the point -3 and 5, which would be right here. And something that you may or may not notice here is that there's actually an invisible line of symmetry with any inverse function and its graph. And this excuse me, this line of symmetry lies along this line here that I'm going to draw in here kind of dotted. And this is just the line y equals x, meaning it's the line that starts at 0, 0 and rises 1 and runs 1, kind of that perfectly diagonal line there. So this would be the line y equals x. And all graphs and their inverses, so this would be the line of symmetry here for an inverse, all graphs and their inverses have this symmetry across that line y equals x. And again, if you're not sure how I graph that, that would be how, it makes sense with slope-intercept form. So up 1 over 1 and starting at 0. But we can see that if we were to fold the one graph on top of the other, they would all have a point that matches it. And you can also see here that, this point is about, sort of a half diagonal away. This one's a half diagonal away on the other side. This one's like 1.5 diagonals away. This is 1.5 diagonals away on the other side. So each point kind of has a corresponding matching point here that matches up with another point on the other side of the graph. And that's just a quick introduction to graphing functions using inverses. If we graph the one function and then we switch our points to alter or reverse the x's and the y's, we should be able to graph the inverse pretty quickly. In the next video, I'll talk about how to actually find the inverse function algebraically.